Hello everyone, and welcome to an introductory lesson on stoichiometry and chemistry. Stoichiometry is one of the most useful concepts a chemist has at his or her arsenal. Stoichiometry essentially is quantifying a chemical equation. So taking the chemical reactions and the chemical equations that we just saw, and taking the molar relationships that we also just saw, and essentially making a sandwich. So just like peanut butter and jelly go great together, so also does chemical reactions and mole ratios. So let's jump right in. The main guiding principle behind all of stoichiometry is the balanced chemical equation. As we learned in the chemical reactions unit, balanced chemical equations can provide us with qualitative information, such as what state of matter something might be in, as well as quantitative information, such as how much product am I going to get. When we have a balanced chemical equation, we use this primarily to support the law of conservation of mass. So again, the law of conservation of mass states that matter cannot be created nor destroyed. It can only change forms. So in a chemical reaction, if we're starting with 10 grams of reactants, we're going to end with 10 grams of reactants. And if I start with 5 atoms of hydrogen, I have to end with 5 atoms of hydrogen. The hydrogen just isn't created out of thin air. It has to come from somewhere. And we can keep that all accounted for using the law of conservation of mass. So here's a chemical equation on the screen. And essentially it shows that when you take hydrogen gas and you add oxygen gas to it, you create water. So we can interpret this a few different ways. We could say on the most simple level, the minimum required amount to make this reaction happen is we have to have 2 molecules of hydrogen gas, 1 molecule of oxygen gas, and when those two things come together, we synthesize 2 molecules of water. Now, where did this 2 molecules and 1 molecule and 2 molecules come from? Well, it came from the coefficients. It came from the ratio of each of these particular molecules that we got from balancing the chemical reaction. Again, our reactants, which are on the left of the arrow, have to equal the products, which are on the right of the arrow. So we have to have 4 hydrogen atoms on the left and 4 hydrogen atoms on the right. We have to have 2 oxygen atoms on the left. We have 2 oxygen atoms on the right. So this works. And again, this is the simplest possibility for this reaction to happen. If I had only 1 hydrogen molecule and 1 oxygen molecule, would this reaction happen? No. I have to have a ratio of 2 to 1 to 2 for this to work. Again, and if I wanted to spit out the ratio really quickly, it's 2, 1, 2. And again, we get that from those simple whole number coefficients that come to the left of each particular formula. Remember, if there isn't a number there, it doesn't mean that it's 0. It means that it's an understood 1. So it's 2 to 1 to 2. Let's say I wanted to do this 10 times. If I ran this reaction 10 times, how many molecules of each would I have? Well, if I did 10 times the amount of this, I would have to have 20 molecules of hydrogen. I would have to have 10 molecules of oxygen, and that would produce for me 20 molecules of water. How did I come up with that? I used the coefficients here to discuss that. So if I did 10 times this, so I did it once and twice and 3 times, all the way to 10, it would be 20, 10, 20. I basically took 10 and multiplied it by the coefficients. But is that ratio changing at all? Did this change to 20 to 10 to 20? No, because when we balance an equation, we want it in the simplest form. So the ratio is still 2 to 1 to 2. Now, in a lab, as you know, from doing the lab we did with the molar stuff, it's very challenging to individually quantify individual molecules. We don't have the tools at our disposal, especially in a high school lab or even introductory college labs, to really identify how many molecules there are. And even if we did have the tools, it would be very expensive and it would not be worth the time. Instead, we use the molar mass to figure it out because we know that for every 1 mole of a substance, that has a set amount of grams, and we can measure grams pretty easily with a scale. So if we think about this ratio of 2 to 1 to 2, instead of thinking of it as individual molecules happening, think about it in terms of moles. I could also say that this would take 2 moles of H2, 1 mole of O2, and that would give me 2 moles of H2O. Is the ratio the same? You betcha. It's still 2 to 1 to 2. But instead of thinking as individual molecules, think of 2 moles of molecules, 1 mole of molecules, and 2 moles of molecules. If you start to see this coefficient relationship here in terms of moles, stoichiometry is going to be very easy for you. Again, the ratio is still the same, 2 to 1 to 2. So we just discussed why this is important, because as you know, in a lab, we use grams to quantify everything. Grams connect to moles. So if I think of the relationship on a macro scale with regards to the reaction, well, if I have 20 grams of this particular reactant, maybe I only need 4 grams of this or 3 grams of this. That's something that we can actually measure. And we can also predict this stuff with math very easily. If we try to think of it in terms of individual atoms, it would take a lot of math and it would be really hard for us to understand and really use, because when we do the scientific notation for Avogadro's number, it's a really, really, really big number. But grams and moles usually isn't too large, so it's very easy for our brains to wrap our head around. Again, to define stoichiometry, that's the study of the mathematical relationships that exist in a formula and in a chemical reaction. Stoichiometry is strictly quantitative. You're not going to be dealing with hardly any qualitative information with regards to stoichiometry. It's going to be numbers, it's going to be measurements. So we have to make sure when you're doing your stoichiometry, you're using your significant figures rules to make sure that your measurements are accurate and representative of what's happening. If we break down the word stoichiometry, it comes from the Greek word stoichion, which means element, and metron, which means measure. And the ry there basically refers to pertaining to. So it's pertaining to the measure of the elements. Let's talk about why this is important. Many of you wake up every morning, you shower, you wash your hair, maybe you use a soap on your body or a body wash. Then after that, hopefully you brush your teeth. You maybe apply some deodorant or some other personal care products. All of those have been formulated by chemists in a lab. And it's very important that this is reproducible. They can make the deodorant and the shampoo and the toothpaste the same every single time. When they take a set amount of reactants, they need to ensure that those exact products that they desire are produced and nothing more or nothing less. Because if there seems to be an increase of mass than what they expected, it's very likely there's probably a dangerous impurity in the sample. So it's very important that we use stoichiometry to really determine whether something's being made safely or not. This also comes with processed foods as well as pharmaceuticals as well, in case you have any medications you have to take. How do we prove that this is true? Well, like discussed earlier, we use the law of conservation of mass. We use that balanced chemical equation. We add up the masses of all the reactants together, and that should equal the mass of products that are created. And if you think about it in terms of an atomic relationship, the number of atoms I have that I'm starting with, I should have that same number of atoms when the reaction is completed. So let's discuss our first type of mole problem, and this is going to wrap up our video today. Mole-to-mole problems are basically the most simple stoichiometric problems, but they are critical in succeeding through this unit and through the rest of chemistry. We're going to use a modified molar map called the Stoichiometrywille Map to complete a lot of these problems. So I encourage you to either print it out or to copy it down into your notes or someplace where you will use it frequently and make it your own. Add some color, add some flair, do what you like. The 3 steps are pretty straightforward to solving most stoichiometry problems. The first step is if they don't give you a chemical equation, you have to figure out what the equation is. So this is kind of familiar to the chemical reactions unit, where they might give you a sentence and they might describe to you in words what's happening. So naming and chemical nomenclature is extremely important to basically write down a chemical equation. Once you have that equation written down, you've got to balance it next. Why do we have to have it balanced? Well, we just saw how important that molar relationship is, or the molar ratio is. So if it's not balanced, your mole ratio is going to be off. And again, the mole ratio that I'm referring to is the ratio of each coefficient for every formula in the equation. Once you have a balanced chemical equation written out, now we do some math, and the math is really straightforward. You basically go from the moles of what you know to the moles of what you don't know. And the relationship is through the coefficients. So if I have 2 moles of this stuff in the reactants, maybe I have only 1 mole in the products. And you can use dimensional analysis to cancel out units, and you figure everything out. In the mole chapter, I really harped on making sure that you guys are specific with your units. So when I say, 32 grams of what? Sodium hydroxide, water, hydrochloric acid, what? The reason why that was so important is because now we're actually going to use that quite frequently. So if you didn't do it in the mole chapter, if you asked, do I really have to do this? You didn't have to do it then, but I'm going to go ahead and say you have to do it now. Let's take a look at an example. Or actually, let's look at the map first. So here's what Stoichiometryville looks like. I know it's a very basic map, but like I said, if you draw it yourself, you can make it your own. For our mole map that we did before, this left side here should look very familiar, and this right side here should look very familiar. We have 4 stopping points, volume of a gas at STP, which the relationship there is 22.4 liters of gas, of any gas, at STP is equal to 1 mole. We know that 1 mole is 6.022 times 10 to the 23rd particles. And remember, those particles can be atoms, molecules, formula units, etc. And then molar mass we're also very familiar with. That comes from the periodic table, and it's unique to whatever the substance is. And this is what we've used before. The only difference is now we're basically doubling it. We're basically copying it on the left side and on the right side, and these 2 moles that are divided up here are different. So this could be, if you think of the example we had previous, this could be moles of H2, this could be moles of O2, this could be moles of O2, this could be moles of H2O. The left side here, or the right, whichever you prefer, is your given substance or the substance you know, and the right side is the substance that you're trying to solve for, or the substance that's to be determined. So let's take a look at a practice problem. Take a minute and read it. It says ammonium nitrate decomposes into dinitrogen monoxide in water. How many moles of dinitrogen monoxide are produced from 2.25 moles of reactants? Okay, well, let's take a look. Step 1, we just discussed. You've got to write down your equation. So to do this, you have to figure out the names, right? Ammonium nitrate, NH4, NO3. The charge is plus to minus, so that's balanced as a 1-to-1 ratio. Dinitrogen monoxide is covalent, so you just write it down how you read it. Dinitrogen means N2, monoxide means O, so it's N2O. Water, as we know, is H2O. So now we have our skeleton equation written here. Again, a skeleton equation is basically the formulas, but it's not balanced. So let's check and see if we have to balance it, and then if we do, how we would do it. So let's look at our nitrogens first. I've got 2 N's on the left of the arrow as a reactant. I've got 2 N's as a product, so the N atoms are balanced. Hydrogens, I've got 4 on the left. I only have 2 on the right. So how could I make that balanced? Well, I'd have to add a 2 here to the water to make that have 4 hydrogens. Now do you see how my hydrogens on the left of my arrow and the hydrogens on the right are equal? Okay, last but not least, I have the oxygen, because now my N's haven't changed. So I have 3 on the left. 1 plus 2 from this 2 that I added would give me 3. So my oxygens are good as well. So this equation is balanced. Now, let's identify the mole ratio. Look at your coefficients. It's a 1 to 1 to 2 ratio. So I would say for every 1 of these, I would get 1 of these and 2 of these. So if you think about it, if I have 2 moles of my reactant here, or I'm sorry, 2.25 moles of my reactant here, and it's a 1 to 1 to 2 ratio, well, if it's 1 to 1 of this stuff right here without doing any math, if I have 2.25 of this, I must have 2.25 of this. And again, if I'm doubling it, well, what's 2.25 times 2? Hopefully you thought it was 4.5, because if it's 2.25 to 2.25 to 4.5. Let's do some dimensional analysis though, just to check our work. So we could set up the problem as follows. If I have 2.25 moles of this stuff right here, I can make a nice conversion factor, because remember, the equivalent statement here is 1 of these equals 1 of these. So for every 1 mole of ammonium nitrate, that is equal to 1 mole of dinitrogen monoxide. Notice the typo I made here. This 2 should instead be written right here. Okay. So if it's a 1-to-1 ratio, if I multiply by 1, divide by 1, the value is still the same. So I would have 2.25 moles of N2O. Now, if let's say I wanted to figure out how much water was there, the question specified dinitrogen monoxide, but what about water? Well, I would just do 2 on top of here. I would put 2 moles of H2O, and I would just do the math. It would be 2.25 times 2 divided by 1. That would give me 4.50 moles of water. Try example number 2 on your own. Pause the video, try it out. Okay, hopefully you read through the video or read through the question and you answered it, and hopefully you got this, but let's go through it together. It says hydrochloric acid reacts with zinc in a single replacement reaction. How many moles of HCl are needed to react with 2.3 moles of zinc? Okay, so again, the first step we have to do is you have to write down your chemical equation. So if you struggled with this or if you didn't come up with this initially, you would have had a bad time. So hydrochloric acid is HCl. Zinc is a solid metal, so zinc would be by itself. Now, if they're telling you this reaction happens and they want to ask you questions as what's generated, you don't really have to check your activity series. But in class, we actually did a lab with zinc and hydrochloric acid, if you remember correctly. And that was the one that really popped and really, fizzled and things like that. So zinc is replacing the hydrogen, so you would have ZnCl2. And again, this has to be balanced because zinc has a charge of 2 plus as a cation, and Cl has a 1 minus as an anion. So it's got to be 2 Cl's to balance out the 2 plus here. And then as we know, hydrogen is a diatomic gas. It's one of those big 7 that we discussed earlier. So it has to be H2 as well. Once you have that skeleton written out, you have to balance it. So you have to put the 2 here, because if you have 2 H's on the left, you have 2 H's on the right. 2 Cl's on the left, 2 Cl's on the right. 1 zinc, it's balanced. So your mole ratio is 2 to 1 to 1 to 1. Again, that comes from the coefficients. So now let's look at the question, what it's actually asking you to solve for and what it's giving you. It tells you have 2.3 moles of zinc, so that's 2.3 moles of this stuff right here. So the question is, how many moles of HCl are needed to react? So essentially, if I have 2.3 of this, how much of this do I need to get the right amount of products here? Okay, so if I'm starting with 2.3 moles of this, and it's a 1 to 2 ratio, essentially I have to double the amount of zinc that I have with regards to the number of moles in order to come up with that answer. So let's set it up with dimensional analysis. If I have 2.3 moles of zinc, for every 1 mole of zinc, which I'm going to put on bottom so these cancel, I'm going to have 2 moles of hydrochloric acid. So 2.3 moles times 2 would give me 4.6 moles of HCl. Thanks for tuning in.